This is the second of two videos on NumPy. In the first, we covered the basics, creating arrays, generating them with arange and linspace, checking their shape, indexing, and transposing. Now we put those arrays to work. We'll run arithmetic across a whole array at once, get into what vectorization means and why it's faster than a loop, and then work through different products: the dot product, matrix multiplication, and the outer product. If you're following along, keep the file from part 1 open. We'll reuse the arrays A, B, M, and N that we made there. So let's start with element-wise arithmetic. We're going to start with regular operators like summation and subtraction. And I'll compute each one. So we have add, and we'll add 2 arrays A, B. And then we have subtract, which is A minus B. And then we have mul, which is A asterisk B. We have division, which is A by B. And then we have power, which is A. And then we can print these. So let's look at what these did. So taking addition, NumPy paired up the elements by position, the first of A and the first of B, the second with the second and the third with the third, and added each pair. So you get 1 plus 4, 2 plus 5, and 3 plus 6, which is what A plus B is. All other operations in this section happen the same way. So we have A minus B, A asterisk B, and A by B, as well as the power. So it's the same position by position logic. This is called an element-wise operation, and it's what all these operators do in NumPy. Two things to note about the result. It's a new array. A and B are untouched by this, and it has the same shape as the arrays that went in. The second point is why shape matters so much here. For this to work, the two arrays have to have compatible shapes. Try adding a 3-element array to a 2-element one, and you'll get a value error telling you the shapes don't line up. Another thing here is the division line. We put in whole numbers and got decimals back. So we have 0.25, 0.5. NumPy automatically switched the result to a floating point type because keeping it as a whole number would have thrown away the fractional part. Let's look at the types a little bit more in depth. D-type is the type of values inside an array. The original array holds integers. The division result holds floats. NumPy worked out that it needed decimals and switched for you. And all of this works just as well on 2D arrays. So let's type that out. Equals summation and then multiplication. So m times n. And then we can print those out. So it does the same thing. It sums up m and n element by element, and it also multiplies m and n element by element. Now, to say plainly what the asterisk does, m asterisk n is element-wise multiplication. It pairs the values by position, in this case 1 with 5, 2 with 6, and so on, and multiplies each pair. That's a really useful operation in its own right, and it's what the asterisk means everywhere in NumPy. The matrix product, rows against columns, is a different operation with its own symbol, and we'll get to that shortly. Before we look at multiplication, we're going to look at vectorization. Vectorization means applying an operation to an entire array at once, rather than walking through it one element at a time with a loop. Here is the clearest version of it. Watch what happens when we combine an array with a single number. We multiplied a whole array by 10 in one go. NumPy applied that single value to every element for us. Same with adding 100. In plain Python, doing that to a list would mean writing a loop. In NumPy, you can do it in a single line. And it scales. Here's 1,000 values with a square root and some arithmetic applied to every single one of them. All of the math happening to the variable big happens in one line with no loop. Now, one important detail about np.sqrt or square root. Notice that we used np square root and not math.square root from the earlier videos. The functions in the math module are built for single numbers. Hand math square root a whole array and it doesn't know what to do. It'll raise an error. NumPy's versions are the other way around. np.square root works on a whole array applying itself to every element, and it works on a single number too. So NumPy's function cover both cases, while maths only cover a single scalar. The rule of thumb is once you're working with arrays, reach for np dot instead of the math one. This bit in the square brackets here is just indexing the first 5 values, the same slicing that we looked at before. 2 reasons vectorization is worth the habit. For those who know what they're looking at, vectorization makes the code clear and concise. And it's fast. The looping still happens, but down in an optimized level rather than in Python, which for heavier math on large arrays can be tens of times faster. The bigger the array, the more it matters. So if you ever find yourself writing a loop over a NumPy array, pause and ask, is there a vectorized way to do this operation? Now we're going to look at multiplication using NumPy arrays. So the asterisk was element-wise. When you want an actual product from linear algebra, there are 3 you'll reach for, depending on what you're multiplying. The first case is when you're multiplying 2 1D vectors, use np dot. B equals np dot a comma b, and then we print it. We get 32. And here's where that comes from. Multiply matching positions of a and b, then add up the results. So 1 times 4 plus 2 times 5 plus 3 times 6. And that's how you'll get 32. That's exactly the same dot product that you've learned in linear algebra. Second, when you want to multiply 2 2D matrices, we're going to use the at operator. So P equals M at N, and then this at symbol is matrix multiplication, rows of the first against columns of the second, the operation that you do by hand in linear algebra. Quick check on this first entry. So the rows of M, 1 and 2, with the first column of N. So 5 plus 14, which is 19. There's also a written out version called matmul. So np.matmul is how you call it, and it's a function. And you would just say np.matmul m comma n. And it's the same as writing m at n. At is just shorthand, and this is what you'll probably mostly see and use. So for matrix multiplication to work, the inner dimensions of the 2 matrices must agree. This comes straight from linear algebra. When you multiply a matrix of shape rows by k, multiplied by another matrix of shape k by columns, the 2 k's, the inner dimensions have to match. So these k's have to match. And the result takes the 2 outer dimensions, rows by columns. Our matrices are both 2 by 2, so they line up fine. But watch what happens when they don't. So now I have a matrix Q with shape 3 by 2, and then I'm going to try to multiply M with Q. So we end up with an error. M is a 2 by 2 matrix. Q is a 3 by 2 matrix. To multiply them, the inner dimensions would need to match, but here they are 2 and 3. So NumPy stops and tells us a mismatch in the core dimension. When a matrix product errors out, checking that the inner dimensions line up is the first thing to do. And one more handy detail, this at symbol only multiplies arrays against arrays. So it won't scale a matrix by a plain number. And that's the job of the asterisk operator, which is what we saw earlier. The third type of array multiplication that we're going to look at is NP outer. This one goes in the opposite direction from the dot product. Instead of collapsing 2 vectors to a single number, it expands them into a matrix. So let's try, let's name np.outer, a comma b, and then we can print these out. So there, every element of A times every element of B laid out in a grid. Think of a multiplication table where each cell is one number times another. And look at the shape. 2 arrays of 3 elements each went in, and a 3 by 3 matrix came out. Where the dot product collapses two vectors to a single value, the outer product expands them into a full grid of pairwise products. And here's a nice way to see that the outer product is really just matrix multiplication in a disguise. If we reshape A into a column and reshape B into a row, then multiply them with add, we get the same grid. So let's do that. So let's say col equals A dot reshape 3, 1, row equals B dot reshape 1, 3, and then we can multiply column times row, and then print these out. It's clear that the output from this reshaping also gives us a result identical to NP-outer. And look at the shapes of A and B now. A is now a column vector with shape 3 by 1, and B is now a row vector with shape 1 by 3. The inner dimensions agree. They are both 1, and the result takes the two outer dimensions, which is 3. So NP-outer is really just matrix multiplication. It reshapes the two vectors into a column and a row first, so you don't have to. For quick reference, the dot product of two vectors is NP dot. Multiplying two matrices, use at as long as the inner dimensions agree. Every pair outer product or pairwise outer product, use NP-outer, which is just column times row. So now for a recap and some important points. The distinction that matters most here in NumPy is the asterisk is element-wise multiplication and at is matrix multiplication. They're different operations and both run mostly without complaint, so mixing them up gives you wrong answers rather than errors. Beyond that, ordinary arithmetic works element by element across a whole array, and that's called vectorization. And the three products each fit a different shape of problem. NP dot for two vectors, at for two matrices when the inner dimensions agree, and NP outer for a grid of pairwise products. In the next video, we'll look at reading data from a file with pandas and formatting the output for effective communication.